Hello everyone, I am Riazul Azim. I am final year MSc Statistics student from Kalyani University. This project is all about the prediction of the car price using multiple linear regression. I have done my project with the help of my classmates, and those are Shayan Sinha and Shourabh Das. Here is the problem statement. A Chinese automobile company, Geely Auto, aspires to enter the US market by setting up their manufacturing unit there and producing cars locally to give competition to their US and European counterparts. They have contracted an automobile consulting company to understand the factors on which the pricing of the cars depends. Specifically, they want to understand the factors affecting the pricing of the cars in the American market, since those may be very different from the Chinese market. The company wants to know which variables are significant in predicting the price of the cars and how well those variables describe the price of the car. Based on the various market survey, the consulting firm has gathered a large data set of different types of cars across the American market. Business goal. We are required to model the price of the cars with the available independent variables. It will be used by the management to understand how exactly the price vary with the independent variables. They can accordingly manipulate the design of the cars, the business strategy, etc. to meet certain price levels. Further, the model will be a good way for management to understand the pricing dynamics of a new market. Here is the data dictionary of the car price assignment data. The data has been collected from Kalyani. Here we observe that the price variable is our dependent variable or response variable, and other 25 variables is our independent variables or explanatory variables. We can see from this data dictionary that car ID is unique ID of each observation, which is integer, and car name is the name of the car company, which is categorical variable, and quite likely is a symboling, which is assigned insurance risk rating, and again fuel type, that is car fuel type. It may be that gas, it may be diesel, which is categorical. Aspirations, which is aspiration used in the car, that is categorical. Again, door number, car body, drive wheel, engine location, that's mean location of the car engine, that is again categorical. Wheelbase, again car length, car width, car height, car width, engine type, again cylinder number, engine size, fuel system, rotor ratio, stroke, compression ratio, horsepower, peak RPM, city MPG, highway MPG. These all are affecting price. Just to see the data dictionary of the car price assignment data. The data consists of 205 rows and 26 columns. The car ID is a unique identifier for each car, so we can ignore it. Our response variable is the price, which signifies the price of the said car. So we will use other variable except the variable car name. So in this way, I remove the two variables from my dataset. Next, we will try to visualize the relationship between the explanatory and response variable. Here it is a matrix plot with the numerical variables. We see that the price is positively correlated with engine size, car weight, car width, car length, wheelbase, whereas there is no such relationship between the car height symboling. Here we also see the kernel density plots in the main diagonal and correlation between the variables in the upper diagonal element of the matrix. Here we are visualizing some categorical variables with box plots, and we observe that the cars with fuel type as diesel are comparatively expensive than cars with fuel type as gas. Second, we observe that engine type OHCV comes into higher price range cars, and again aspirations for turbo are comparatively priced higher than STD. Here we like to see the Pearson correlation between the features. We observe that the price is highly correlated with horsepower, engine size, car width, we also observe that the car width is highly correlated with car length and wheelbase. And we also observe that the data suffer from the multicollinearity problem. Next, we come to missing value and outlier detection step in the modeling. There is no such outlier in the data that might affect the modeling. We observe this from the percentile table of each numerical variable. There is no missing value in the car price assignment dataset. Cleaning the dataset. Before we go further, first we need to make sure that our dataset is clean and will be useful. If we watch closely, there is some problem with the categorical variable. Look at the cylinder number variable in the slide. There are some categories with only one instance, such as machine with 3 cylinder number and 12 cylinder number. This information may not be too useful for use, and we can consider them as a noise. Furthermore, this will cause problem during train test data split, where we will not find same category in either one of the datasets. Same problem can be found in fuel system and engine type variables, so we need to filter and select categories with number of instances that greater than 3. Let's take this as a threshold. Before we make the model, we need to split the data into trained dataset and test dataset. We will use the trained dataset to train the multiple linear regression model. We will use 80% of the data as the training data and the rest of it as the testing data. Now we will fit the linear regression model using price as the response variable in the training data. Next, we will like to remove non-significant variable from our dataset and again building the model. The summary of the first model shows a lot of information, but for now, we may better focus on probability that greater than mod of t. This column shows the significance level of the variable towards the model. If the value is below 0.05, then we can safely assume that the variable has significant effect towards the model, meaning that the estimated coefficient are no different than 0 and vice versa. Thus, we can make a simpler model by removing variables that has p-value that greater than 0.05, since they don't have significant effect towards our model. The estimate value shows the coefficient of each variable. So, the first model with complete variables has adjusted R-square of 0.9032, meaning that the model can explain 90.32% of variance in the target variable, that is car price. And meanwhile, our simpler second model with removed variable has adjusted R-square of 0.9001. No big difference with our first model. This shows that it is safe to remove variable that has no significant coefficient values. Next, we like to see the Pearson correlation matrix in our second model and remove the variable with strong correlation among explanatory variables. Based on the correlation matrix, engine size has a strong correlation with other variables. We will remove the variable and see if autocorrelation is present in our model or not. After removing the variable with strong correlation among explanatory variables and again building the model, third model has adjusted R-square of 0.8804 and multiple R-square of 0.8904 in the training dataset, which is quite good. Next, we like to detect multicollinearity using generalized variance influence factor (GVI). To make GVIs comparable across dimensions, it is suggested to use GVI full to the power 1 by 2 into degrees of freedom, where degrees of freedom is the number of coefficients in the subset. This reduces the GVI to a linear measure. A cut-off GVI full to the power 1 by 2 into degrees of freedom value of 2.5 is used by most business because it offers a more significant and clear rule. And here we check the GVI full to the power 1 by 2 degrees of freedom in our third model for odd variables, which is quite good. Assumption of multiple linear regression. First assumption: linearity and additivity of the relation between dependent and independent variables. Second assumption: statistical independence of the errors, in particular no correlation between consecutive errors in the case of time series data. Third, homoscedasticity, that means constant variance of the errors. Fourth, normality of the error distribution. Check linearity and homoscedasticity assumption in our third model. On the fitted versus residual plots, we see two things very clearly. For any fitted value, the residuals seem roughly centered at C. That is good. The linearity assumption is not violated. To assess if the homoscedasticity assumption is met, we look to make sure that the residuals are equally spread around the y that equal to 0 line. Again, the homoscedasticity assumption is not violated. This is good. Check statistical independence of the errors assumption in our third model. If statistical independence of the errors assumption is violated and error term observation are correlated, autocorrelation is present. From Darwin-Watson test, we observe that p-value greater than 0.05. So we can conclude that autocorrelation is not present and statistical independence of the error assumption is not violated. Checking normality assumption in our third model. The QQ plot of residual can be used to visually check the normality assumption. The normal probability plot of residual should approximately follow a straight line. We also check the histogram of the residual for detecting violation of normality assumption. We observe that normality assumption is not violated. We take our third model as the final model, and this is our measure of model performance. Multiple R-square for training dataset is 0.8904. Adjusted R-square for training dataset is 0.8804. AIC for training dataset is minus 368.3565. DIC for training dataset is minus 322.5128. Multiple R-square for testing dataset is 0.9711. Adjusted R-square for testing dataset is 0.956. Training dataset has RMSE of 2402.212 and testing dataset has RMSE of 2252.844, which is quite good. Conclusion. Variables that are useful to describe the variance in the car price are aspiration, engine location, car weight, engine type, cylinder number, stroke, peak RPM, price. Our final model has satisfied all the classical assumptions. The adjusted R-square of the model is high, with 88.04% of the variable can explain the variance in the car price. The accuracy of the model in predicting the car price is measured with RMSE. With training data has RMSE of 2402.212 and testing data has RMSE of 2252.844, suggesting that our model is not overfitting the training dataset. Last but not least, thank you Dr. Ganesh Dutta for your valuable guidance and support.